Welcome dear students. We are covering the topic isomerism, and in the previous lectures we have discussed the isomerism, structural isomerism and types of the structural isomerism including chain isomerism, ring chain isomerism, functional group isomerism, position isomerism and metamerism. Now this one is the fifth lecture about the isomerism in which we are going to discuss another type of the structural isomerism, that is the tautomerism. We will be discussing tautomerism in detail, the different types of the tautomerism, conditions and characteristic features of the tautomerism as well. Now the word tauto is from Greek, which means same, and mer, it is again from Greek word meros, which means part. So the term tautomerism, it literally means the same part, and it is common in all types of the isomerism that the same part is basically the molecular or empirical formula of isomers. A compound has usually two parts. One is its molecular formula and other is its structural formula. So the isomers, they have one part in common, and that one part in common, it's their molecular formula, means they have same molecular formula. You can say same empirical formula, and because the molecular and empirical formula are same, so their molecular mass and empirical formula mass will also be same. Now, what is actually tautomerism? Let us define tautomerism. Tautomerism is a concept that describes the presence of two compounds which are interconvertible due to relocation of a bond or atom within a compound. So, tautomerism is basically the concept which describes that there are two compounds which are obviously isomers of each other. They exist and they are interconvertible, mean one tautomer or one isomer can be converted to the other, and this interconversion is either due to the relocation of a bond or, dear students, relocation of an atom, and that relocation will be within a compound, means a bond will either relocated or an atom will be relocated within a compound, and when this relocation takes place, then the second isomer forms, second compound forms. Because they are interconvertible, so usually they exist at the state of dynamic equilibrium, mean one isomer is easily converted to the other and the dynamic equilibrium exists between the two tautomers. Now dear students, very important thing, In relocation of a bond or relocation of an atom takes place within a compound and tautomerism arises or tautomers arise. So relocation of a bond gives rise to the type of the tautomerism which is called as valence tautomerism. Mean the type of tautomerism in which tautomers form due to relocation of a bond, that is called as the valence tautomerism, and the type of the tautomerism in which relocation of atom occurs and that atom is usually hydrogen nucleus. And you know hydrogen nucleus or H positive, that is also called as the proton. So that's why this type is called as the prototropy. So tautomerism has basically two types. One is the valence tautomerism and other is the prototropy. In valence tautomerism, the tautomers arise due to the relocation of the bond within a molecule or within a compound. And in prototropy, the tautomers arise due to the shifting of the proton or relocation of the proton H positive ion within a molecule. That's why, my dear students, keep in mind that tautomerism is given as two names. Main tautomerism is also called as the desmotropism or prototropism. So these are two other names of tautomerism. Mean tautomerism may also be called as the desmotropism or prototropism. What does it mean? Dear student, desmo refers to bond. In Greek, desmos means bond, and tropism shows movement or relocation. In biology, the students they study tropic movements. So tropism basically refers to the movement. So desmotropism means movement or relocation of the bond, and that type of the tautomerism which occurs due to the relocation or movement of the bond mean valence tautomerism. It is also called as the desmotropism. On the other hand, that type of the tautomerism which arises due to movement of proton. Proton means H positive ion or proton, and tropism again that refers to movement. So prototropism means movement or relocation of the proton, and the second type of the tautomerism in which tautomers arise due to the relocation of proton, that is called as the prototropism. So referring to this definition, we can conclude that from this definition we can say tautomerism is of two types. One is the valence tautomerism or desmotropism due to the movement or relocation of the bond within a molecule and the tautomers they arise. And the second one is the prototropism or prototropy. It is due to the shifting of the hydrogen H positive ion within the molecule and the second isomer arises. So this was about the definition and the name of the two types of the tautomerism. Now dear students, in order to make this concept somewhat clear, let us consider some examples of tautomerism. The first and very common example, that is this one is an amino acid. You know, it is the building block of the proteins. It has an amino group or carboxyl group which is acidic in nature, so that's why it is called as the amino acid. Now dear student, what happens? This nitrogen is a basic group. You know, nitrogen has lone pair of electrons, so it acts as a base. It will attack on this slightly acidic hydrogen of the carboxyl group, and this hydrogen will break its bond with oxygen and it will move out of this molecule as H positive ion, and nitrogen is a NH2 group is a basic group, it will accept proton. So this structure arises. This is called as zwitterine. Swiss word means both because it has both positive and negative charges, so that is why it is called as the zwitterine. Now this amino acid and this zwitterine, they are tautomers of each other, and because this tautomerism has arisen due to shifting of proton within this molecule from one atom to the other atom, that's why these types of the tautomers are protoisomers or prototropism is shown here. So that is an example of the prototropy. Basically this is example of this type of the tautomerism in which there are more than two compounds which are interconvertible due to the relocation of hydrogen atom within a molecule, and they exist at the dynamic equilibrium because the process is reversible, and you know the fate of all the reversible processes is to attain the dynamic equilibrium. So this example is particularly that of the prototropy. This example belongs to the type of the tautomerism which is basically prototropism or prototropy. Now let us take another example. This compound is an enol. En is because of carbon-carbon double bond here, and Ol is due to presence of the hydroxyl group. Alcohols, they end at Ol. Enols are usually unstable, and what happens that this hydrogen moves in the form of H positive ion. This bond, pi bond shifts to carbon. Carbon gets negative. This hydrogen becomes positive because it is removed in the form of H positive ion or proton. What happens that so simply this hydrogen relocates to this atom from this oxygen atom, and this one is acetaldehyde, you know, it is basically an aldehyde. And what is the name of this compound enol? That will be called as the ethanol. It has two carbons with double bond, that refers to ethene, and OH group refers to alcohol ol, so that will be called as the ethanol. Now why this is unstable and it is changed to a stable form which is acetaldehyde? Because dear students, you know carbon-carbon double bond is weaker as compared to carbon-oxygen double bond. Carbon-oxygen double bond has more bond energy as compared to carbon-carbon double bond. So that's why acetaldehyde is more stable as compared to the ethanol. And when the dynamic equilibrium will be achieved, then no doubt in that mixture the amount of acetaldehyde will be greater as compared to the ethanol because it is more stable. And which tautomer will be dominant at the time of dynamic equilibrium? It also depends upon the external conditions like temperature, like the solvent in which you have moved these compounds. So that also decides that which component will be dominant in the dynamic mixture. So again, the proton is shifted, relocation of proton from this hydrogen to from this oxygen to this carbon, and that has resulted in the another type of the isomerism, that is the tautomerism. And these ethanol and acetaldehyde, they are tautomers of each other, and this also belongs to the type of the tautomerism which is called as the prototropy or prototropism. So these are the two examples of the prototropism. Now let us consider some more examples, like one of the most important type of the tautomerism, that is keto-enol isomerism, in which again there is an enol. It is unstable, and it changes to a stable form which is acetone. It is stable. How this conversion takes place? Again, this hydrogen is relocated to this carbon. Hydrogen moves to this carbon and double bond shifts here. So that's why that will be acetone. It is its stable form. Now this isomerism is called as keto enol isomerism, because here the dynamic equilibrium exists between a ketone and an enol. So that is called as the keto enol isomerism. And when the dynamic equilibrium under normal conditions, room temperature and pressure, that is achieved, there is only 0.001% of enol in the mixer, and 99.99% acetone is present in the mixer of the dynamic equilibrium or equilibrium mixer. Why? Because acetone is more stable. Why acetone is more stable? Because of the electron donating effect of these two alkyl groups, and due to stability of this carbon double bond oxygen. And carbon double bond oxygen, as I have already told you, it is more stable as compared to the carbon double bond carbon. And this is the most important form or most important type of the tautomerism, which is called as the keto-enol isomerism. Now, my dear students, let us move towards the next example. Next example is basically a nitrogenous base. Now this nitrogenous base, that is uracil, and it is part of the RNA, nucleic acids. Now this one is lactam form. Lactam is basically the cyclic amides. It is a cyclic amide. You can see that it has ring and the amide functional group. Now it is converted to its tautomer. This is lactam form, Lectin form is basically hydroxyimide. You can say that this one is the amide linkage and these are two hydroxyl group, so they are hydroxyimide. Now this one is the nitrogenous base uracil, and again the shifting of the hydrogen atom has taken place from this nitrogen to the oxygen. So that is again the prototropism, and this prototropism has taken place in a cyclic structure, so sometimes it is also called as the annular tropism. The type of the tropism which takes place in the cyclic structure in which the hydrogen moves within the molecule and the second compound exists, that is called as the annular tropism. So this is again an example of the annular tropism. And this lactam form and lectin form, again they are interconvertible. These two tautomers are interconvertible, and the final fate will be that they will exist at the state of the dynamic equilibrium. Now let us take some more examples, like in the amides. There is a very famous structure, this one is an amide, and specifically it is called as acid amide. Now again what happens, let us write down these hydrogens separately to make the concept more clear. Oxygen, through its lone pair, it attacks on this hydrogen, and hydrogen shifts the bond towards this nitrogen. What will happen, that this amide will be converted to imide. So this one is the amide form and this one is the imide form. It means that amide and imide, they also show the prototropism, that is the movement of a hydrogen atom. But this is in a straight chain compound, so that will not be called as the annular tropism. That will be called as the simple tropism or tautomerism, because annular tropism is the movement of the proton within the cyclic structure from one atom to the other atom. Similarly, let us take the last example. Here is nitrogen, and this one is NH2. It is converted to, now this nitrogen attacks on one of the hydrogens of this NH2 group, and it will result in the NH. Now this one is amine form due to this NH2 group, and this one is amine form. Again the hydrogen has shifted from one nitrogen to the other nitrogen, and that will also be called as the tautomerism, and it will belong to the type of the tautomerism which is called as the annular tropism. So these are some examples of the tautomerism. Now there is another very important example, which is the basically glucose when it is changed to its cyclic structure, that is ring chain tautomerism. This is D-glucose. And you know, glucose in the straight chain, it is somewhat unstable. So when you dissolve glucose in some polar solvent, then that is changed to the ring structure. Glucopyranose, that is the pyranose ring, six cornered ring with one oxygen on one corner. Sorry, on the third carbon you will change the location of OH. H. So this one is glucose in the straight chain, and this one is glucopyranose, and this one is in the ring structure. So again the shifting of proton takes place and glucose is changed from straight chain structure to the pyranose ring. Pyranose ring means six cornered hexagonal ring, and at one of the corners of that ring there should be oxygen atom. That ring is called as the pyranose ring. And this one is an example of ring chain tautomerism, which is again a type of the prototropism. So glucose and glucopyranose, they are ring chain tautomers of the each other. So these were different examples in which you have seen the prototropism, because we are discussing the type prototropism here. So you have seen the examples of the prototropism, that how hydrogen transfers from one atom to the other atom within the molecule, and the tautomers, they exist at the dynamic equilibrium. Now my students, after examples, do all the compounds they show tautomerism? We say no. There are certain conditions and characteristics of tautomerism. Now what is the condition? Condition is that the compound should be polar and it should have a weak acidic functional group. A compound which is polar and it has weak acidic functional group, only that compound will show the tautomerism. Just like we will again write down the structure of the amino acid here. Now this amino acid is polar due to carbon oxygen bond, carbon nitrogen bond, oxygen hydrogen bond, nitrogen hydrogen bond. This is basically a polar molecule, and it again has a weak acidic group. So this molecule, that will show the tautomerism. Only those compounds show tautomerism which are polar and they have slightly acidic functional group. Now recall all those examples that I have written here. You will find polarity and a weak acidic functional group in every example that I have quoted here. Now what are the characteristics of the tautomerism? Basically, tautomerism is relocation, and relocation of either a bond or an atom and that relocation of bond or atom should be within compound or within molecule. Then tautomerism does not affect bond lengths of the compounds, mean when one bond is shifted within the compound or one atom is shifted within the compound, the overall bond lengths they remain same. Similarly, tautomerism takes place in both planar and non-planar molecules. So it does not depend whether the molecule is planar, mean all the atoms are present within the same plane, or non-coplanar, in which all the atoms are not present in the same plane. In both cases, tautomerism takes place. So condition is this one, and these are the some characteristic features of the tautomerism. Now, very important point. What is the difference between resonance and tautomerism? Some people they confuse resonance and tautomerism, so it is very important that we must mention the difference between the resonance and tautomerism. Dear students, let me draw first of all two tautomers. This one is amino acid. It exists with this zwitterine. These are two tautomers, and now the resonating structures. I will draw the resonating structures that you commonly study in your FSC. Some of the resonating structure of the benzene, Cacule and Dever structures. Now, my dear students, what is the difference between resonance and tautomerism? The first difference is that the reason of both these that is different from each other. Please take the copy and pencil and write down the differences. Number one is the reason. Tautomerism arises due to relocation of the bond or atom, but resonance arises due to the movement of the delocalized electrons. So that is due to the resonance is due to the delocalization of electrons, and tautomerism is due to the relocation of the atoms or the group of atoms or bonds. Second, existence. Do these resonance structures of benzene they actually exist? We will say no. These are the hypothetical or theoretical structures that lead us towards the actual structure of the benzene. There is no practical existence of any of these structures. They are just proposed structures or theoretical structures that lead us towards the actual structure of the benzene. But these are two tautomers. One is the amino acid, other is the zwitterine. They practically exist. They actually exist in the equilibrium mixture. So there is actual practical existence of these two structures in the equilibrium mixture, but all these structures they are hypothetical. So resonance structures are basically hypothetical, proposed structures to explain the actual structure of some compound. But the tautomers, they are not the hypothetical structures or hypothetical molecules. They are the actual compounds or molecules that actually exist in the dynamic equilibrium mixture. The third one is stability. Resonance has a great concern with the stability of the compound. Greater the resonance structures, greater the number of resonance structures actually of a compound, greater is its stability. But tautomerism has nothing to do with the stability of the compound. No doubt that a form is changed to the more stable form, but overall stability that is not decided by the tautomerism. So tautomerism has nothing to do with the overall stability of the compound, but resonance that deals or that has concerns with the stability of the compound. So there are some major differences. Let me recall if there is some other difference between the, yeah, the last one, fourth one is the bond length, which I have already mentioned that the tautomers they have almost same bond lengths, but you can say in the resonating structures the bond lengths they are different. So as a result of resonance, the bond lengths they change, but as a result of tautomerism, there is no overall effect on the bond lengths. So that is the basic difference between the resonance and tautomerism. So my dear students, in this lecture we have covered the only one type of the tautomerism, which is the prototropy, or you can say prototropism. In the next lecture we will be discussing the valence tautomerism, what is the valence tautomerism, and we will also discuss some examples of the valence tautomerism. In case if you feel any problem in this lecture, do mention your problem or question in the comment section. I will definitely reply them. Take care.